Good morning to one and all. My name is Shifa Ayaz. I'm a third year electronics student, and today I'm going to teach you my sixth experiment, that is design of a comparator, zero crossing detector, time marker, and a sample hold circuit. So let's begin with the article. So the basic very first part which we are going to start is with the design of inverting and non-inverting comparator. So the basic use of a comparator is that uh, we apply two voltages, that is, one is your input voltage and the other voltage which we are feeding is the reference voltage, and the output is such that the output is the comparison between the two voltages, and the largest of the two voltages is uh, is seen at the output terminal. So let's see here. So in inverting comparator, what happens is that when my V in is less than the V reference, I would be getting a plus V sat output, and when my V in is greater than V reference, I would be getting a minus V sat at my output. So let's actually check it out with the practical itself. So launch your LT Spice and yeah, make the inverting comparator circuit where the input is applied at the inverting terminal and the positive terminal is fed with the V reference voltage. Now since I'm having a 5 volt peak to peak voltage, so I'm gonna give 2.5 as my input voltage. V reference I've considered to be of 2 volts, and this is the basic circuit how it looks like. Now I'm gonna run the circuit and check my output. So click on the V in and V out. So just let me check. So when your V in is less than the V reference, you would be getting a plus V sat, which is 4.07. Okay. And when your V in is greater than V reference, it would be reading as 10.092 volts. Okay, so here we can check that in our practical observations. Okay, so this is for an inverting comparator. Now since I have considered a 10 kilohertz, so my output would be switching from these two ranges, that is from 10.08 to 14.07 volts, and for V in being greater than Vref, it would be from 14 to plus 10.08 volts, which is being observed. So when I'm doing this experiment at lower frequencies, this is what I'll be getting at my output, and as my frequency increases, I would be getting my VSAT in ranges like this, as I've shown you for 10 kilohertz. Similarly, at 50 and 1K and 5K, you will be observing these values. Now let's move on to the next part of the experiment, that is the non-inverting comparator. So open the non-inverting comparator. Yes. So here what I've done is, now I've applied the input at the positive terminal, that is my V in is applied to at the non-inverting terminal, where I've considered 5 volt peak to peak input voltage. So I've been applying 2.5 volts and frequency to be of 50 hertz. V reference is of 2 volt, which is applied to the inverting terminal, and the same parameters have been kept as before. So now let's run the circuit again and check the output. Okay, so once you click on your input and the output, so this is what you get. So similarly, as I said, when my V in is less than 2 volts, so the output would be positive saturation, that is plus Vsat. And when my Vin is greater than 2 volts, it would be minus Vsat. So that can be verified when you place your cursor. So this is for negative when my Vin is greater than V reference, it is minus 14.0 volts, and when my Vin is less than 2 volts, it is 14.07. So that's how you take your readings. So this is done for the non-inverting comparator. Now for a zero detector circuit. The zero detector circuit, let me show you the circuit. Okay, zero crossing detector. Again, there are two types in this detector, that is inverting and non-inverting. Here I've designed an inverting zero crossing detector, so the input is fed to the inverting terminal. The positive terminal is grounded directly. Okay, so uh, this circuit is used to get either positive. Okay, so let's simulate this circuit and check the output. So yes, okay. So over here, what is that? Again, the same analogy is being implemented over here. When your V reference is greater than the applied voltage, so your output would be positive saturation, which reads out to be 14.07, and your when your Vref is less than Vin, it would be negative Vsat, that is minus 14.07. So this is again seen, this is a bit advanced version of your comparator circuit, and this circuit is usually used to drive LEDs or to control the gate voltage. So based on the when your input crosses this zero voltage, according to it your output would be switching from minus Vsat to plus Vsat, so which is observed over here. Moving on to the next part, that is the time generating circuit. So let's open the time marker circuit. So again, this circuit, this is a zero crossing detector, which is a non-zero crossing detector over here. I have a capacitor and two resistors connected with a diode. This circuit is usually used to get positive or negative spikes at your output. Now, since the diode is connected in this forward direction, so the output would be positive spikes. If I connect my diode in the reverse direction, I would be getting negative spikes at my output. So now let's run the circuit and check the output. Okay, so now I'll plot my sinusoidal wave, that is the input waveform, and the output over here. So here you can see I'll change the color over here so that it is more visible. Okay, yes, so this is the positive spikes which is produced due to this RC network over here, and this positive spike I'm getting is due to the diode placed in the forward direction. Once I reverse the direction of the diode, I would be getting negative spikes at my output. So this is how your time marker circuit works. Now moving on to the sample and hold circuit. Okay, so this is my sample and hold circuit. Here I am using two op amps over here, that is OP07, and an N MOSFET is being used over here to which is via which I am feeding my pulse, that is my square wave, that is my square input waveform, and a capacitor is used for the charging, for the sampling and holding part, which I'll be showing you all over here. So when the N MOSFET is turned on, this so the circuit is in a so the circuit is basically like a closed switch. So my capacitor charges up to a specific amount of time, and once when my uh, N MOSFET is turned off, when there is zero voltage available at over the input terminal of this um, N MOSFET, so the output so the capacitor cannot directly discharge over here due to the high impedance of this op amp. So the capacitor now holds that particular amount, holds that voltage for some amount of time, which is referred to as the holding time. So and the duration and the time for which the input voltage is sampled is known as the sampling period. So this is how your sample and hold circuit looks like. So when the MOSFET is turned on, the capacitor charges up to a certain up to the peak voltage, and when the N MOSFET is turned off, the capacitor cannot discharge directly. So due to the high impedance offered by this op amp, so the capacitor now holds that charge for some amount of time. So that uh, so that uh, so that is known as sampling and hold circuit, where I am sampling as well as holding the charge. So let me show you the output. So this is how you build the configuration of your circuit and click on run. So again I would be seeing the I would be actually adding a plot pane over here again. So the first which I'm plotting is the pulses, that is my square waveform which I'm applying to the MOSFET, and at this I'm gonna plot the sine waveform, this sine waveform which I'm actually gonna sample. So this is my sine waveform, and the sampled output of this sine waveform would be taken out from the Vout section. So this is how your sampled output looks like. So it charges up to the peak value, and since as I said it cannot discharge directly due to the high impedance offered by this op amp, it holds the charge for a specific amount of time, and then again when the circuit is turned on, that is when again I've applied the pulse at the N MOSFET. So again the capacitor starts charging to its peak value. So this is how the process is done, and you see the sample and hold output at the out sample and hold output of this circuit is observed over here. To get a better output, sampled and hold output, you can use LTC6244 op amp, which will give you a better sampled output of this same circuit. So due to the high slew rate offered by the op amp, you would be getting a better amount of sampling at the output. So that's all regarding to the explanation with this experiment. Thank you.